Hello, everyone, and thank you for attending today's webinar, Embracing Wi-Fi 7, the Future of Enterprise Wi-Fi Deployment, sponsored by HFCL. Before we begin, I will cover a few. On the left-hand side of your screen is the Q&A. If you have any questions during the webcast, please type your question into the Q&A box and submit the questions to our speakers. All questions will be saved, so we don't get an answer. If you have any technical difficulties, please click on the yellow help widget. Here you can find answers to common questions. So a copy of today's slide deck is available for download in the green resource list widget. Near the end of today's presentation, please take 1 minute to complete the survey. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience console that was sent to you earlier today. I would now like to turn over the event to him.
Okay, thank you, Catherine. I believe you just handed over to me. Your audio was breaking up a little, but let me just check. Nadeem, can you hear me?
Yes, I can.
Okay, perfect. So hello, everybody, and welcome. Terrific to have you on today's webinar, Embracing Wi-Fi 7, the Future of Enterprise Wi-Fi. Wi-Fi 7, of course, is one of the most kind of talked about, hottest wireless access technologies in residential or enterprise, or in fact in carrier environments this year. We're going to be drilling down into enterprise Wi-Fi, where some of the new capabilities are going to be proven to be, I think, super useful in some of the more demanding use cases that you might see coming up over the next few years. As you heard, my name is Gabriel Brown. I'm Principal Analyst with Heavy Reading, where I lead our wireless network coverage. I am your host and moderator for today. I'm joined by our expert guest speaker from HFCL, Nadeem Akhtar, who's VP Product Line Management over there. Nadeem, great to have you on the call. Really looking forward to it. Could you give us a little bit of background on who you are personally and on HFCL?
Thanks, Gabriel. My name is Nadeem, and I work for HFCL. I've been part of the Wi-Fi industry for almost a decade now. Started in operations role, moved to R&D, and at the moment I head the Wi-Fi product team at HFCL, responsible for Wi-Fi 5, Wi-Fi 6, and Wi-Fi 7 products. So that's my background. HFCL is an India-based company with a global presence across 60 plus countries with products ranging from passive optical all the way to active networking for enterprise, telcos, and a whole lot of other verticals. So that's a quick intro about HFCL.
Just give us a little summary of where you're at in the enterprise Wi-Fi market.
So HFCL started making Wi-Fi access points only a few years ago. In the last few years, we have established our presence across multiple verticals, including education, carrier Wi-Fi, banking, in stadiums and venues, and in many other domains. And as I said, we are present, particularly on the Wi-Fi side. We are present, obviously, because of our India-based company. We have a strong presence in India across government, in finance. One of the largest banks in India is using our Wi-Fi. In federal, we have a very strong presence in India. And Reliance Jio, which is the largest operator in India for mobile communication services, has deployed a massive mobile data offload network using HFCL equipment. So these are some of the customers that I can talk about. And in internationally also, as I said, UK, we have a presence in Australia, in Japan, parts of Africa, Middle East, as well as in Russia. So these are some of the places where we have Wi-Fi deployments using HFCL access points.
Okay, terrific. A useful backgrounder, I think, from the call. I'm looking through the list of people on. There's a load of people on, and they're from all over the world. So it's good to get a level set on that. I think one thing to say about Nadeem, he's got a brilliant presentation coming up, but he is also really open to taking questions. And we're going to have a pause about halfway through for a few of the technical questions, and then we'll deal with the rest at the end. If you do have a question for him, use the Q&A box on your screen, and I'll be keeping an eye on those on the back end. Probably won't be able to get to everything, but I do encourage you to do that. I know that Nadeem is open to taking them. So a very quick agenda. I'm going to give a really short introduction, one slide, in fact, today. Nadeem will take us through the bulk of the material. We are going to pause as well as for some questions for a poll question, an audience poll. You'll see that coming up, and then aiming to leave a decent amount of time for some Q&A at the end. Now, just by way of introduction, I thought we'd just have again a bit of a level set on the enterprise Wi-Fi market. This is using some data from my colleagues at Omdia, who track this market on a quarterly basis. Very detailed set of numbers and forecasts, and you can cut it all different ways. This is kind of a high-level view. I think the first thing to say is, enterprise Wi-Fi, WLAN as we call it here, it is really a high-volume market. We think there's somewhere around 40 million enterprise APs shipped per year globally. That's a big number. It's not residential Wi-Fi numbers, but it's a very big number in enterprise networking, and that's actually grown a bit in 23 and 24 with the Wi-Fi 6 coming in. Wi-Fi 6, of course, is the dominant technology in the market, and it's going to Wi-Fi 6E in some places. Pretty straightforward. We're going to go to 7. On the left here, I'm showing the top 5 verticals by revenue share. So this isn't units now, but by revenue share. You can see the top 5 are actually pretty closely clustered with education, government, manufacturing, retailer, and finance all there. The other section's pretty big, 41%, but there's some major sectors there. We're thinking about things like healthcare, service provider, and a bunch of others. So it's pretty well distributed really across the economy, whichever country you are in. Now, aside from the technologies and the ins and outs of the air interface and all these kinds of things that we'll get into, one of the things, having covered enterprise Wi-Fi, WLAN, as we used to call it from, back a couple decades or more now, the number one thing really for most customers, most enterprise customers, comes down to the operating model. How do they deploy it? How do they manage it? How do they run it? The different tooling you have, whether it's a managed service, whether you have cloud ops, there's a whole bunch of stuff that comes into that. So we are going to start with the technologies, get into some detail on technology, but it's going to bring up to like how you actually deploy and manage this and make it work for your business as well as we go through. So stay tuned for that. All really remains is for me to hand over to the first slide and give the controls to Nadeem. Please take it away.
Thanks, Gabriel, while the slide is coming up. So as Gabriel said, we are going to talk about Wi-Fi 7, and in particular, I am going to talk about the three areas. One is from a technology perspective, what are the key features of Wi-Fi 7? What Wi-Fi 7 means for enterprise deployments, and how it addresses the problems of specific industry verticals and the applications that are part of those verticals. So we'll talk you through these 3 areas. So before I go into Wi-Fi 7, a quick look at what has happened over the last 2.5 decades with respect to the enterprise Wi-Fi. So Wi-Fi today is the dominant technology when it comes to enterprise networking. And as a result, the expectations from Wi-Fi are very high. Customers expect very high throughput, the ability to support a large number of concurrent connections, a very low latency, and for mission critical applications, very high reliability as well. In addition, robust security and seamless mobility are also critical for any enterprise network. And as we see Wi-Fi being deployed in many more challenging scenarios, there is also demand for extended range. So we'll see how some of these problems have been solved in the current generation and the next generation, which is Wi-Fi 7. So if we look at how Wi-Fi technology itself has evolved over the last 2.5 decades, there have been a lot of changes since the days when Wi-Fi was really basic complement to wired networking. And these changes have been brought about, I would say, in 3 key areas from a wireless perspective. The first one is the air interface itself has undergone transformation in the form of more advanced modulation schemes being introduced, which allow us to push more bits per second per hertz. Then we have the advancements in the multi-stream and multi-user technology, which allows us to push more data across special streams using MIMO, and also the ability to multiplex users across frequency domain, time domain, and spatial domain. And last part is on the spectrum front, we are seeing now more spectrum being available for Wi-Fi, especially with 6 gigahertz coming into the picture. And also the channel bandwidth has evolved. Obviously, channel bandwidth, more bandwidth you have, the higher data rates you get. So as a consequence of these enhancements that we have seen over the last 25 years, we can see that there has been a significant jump in the peak data rates that are possible over a Wi-Fi link. And we will see, how these are getting further pushed through the new advancements that we have in Wi-Fi 7. So before we go into Wi-Fi 7, let's take a quick look at what happened in Wi-Fi 6 and 6E. So unlike previous generations of Wi-Fi, at least until Wi-Fi 5, where there was a lot of focus on pushing the peak rates to as much as possible, Wi-Fi 6 tried to put more emphasis on efficiency improvements. In particular, being able to increase the spectral efficiency, by which we mean that the ability to send more bits per second per unit of spectrum, typically measured in bits per second per hertz. So in Wi-Fi 6, we had a more efficient OFDM symbol design, which allowed us to pack more data. We had 1024 QAM, which was higher order modulation compared to Wi-Fi 5. And then we have advancements in MIMO. In particular, multi-user MIMO in uplink and downlink, which allowed multiplexing of users with the same channel bandwidth. So you could now pack in more users using the same bandwidth. So this allowed us expansion in capacity and also more spectral efficiency. Then on the high density requirement side, we had OFDMA, which was capable of supporting multi-user transmissions in frequency domain. So which complemented MIMO, which allowed multi-user transmission in spatial domain. So with a combination of OFDMA and MU-MIMO, now you could schedule a large number of users in the same transmission. Spatial reuse was very critical when it came to high density deployments where a large number of APs are packed in a small space. So it allowed better reuse of frequencies. And then with 6 gigahertz, we now had access to totally new band of almost 1200 megahertz if you look at US, and at least 600 megahertz if you look at many other countries like UK and Europe. And with this new band, had two advantages. One was that it is relatively cleaner in terms of interference, because most of it is being used by point-to-point links for backhaul and so on. And second is, with a wide swath of spectrum available, you could really now use wider channels like 160 megahertz and 80 megahertz, which was theoretically possible in 5 gigahertz, but we always had challenges getting a contiguous 80 megahertz or 160 megahertz. So these three enhancements in Wi-Fi 6E allowed us to support much higher number of clients and much more denser deployments in terms of number of cells. From a coverage or a range perspective, again, because of different symbol design, we could now support longer or larger cells and higher reliability at the cell edge, thanks to the extended range PPDU and also the dual carrier modulation scheme supported in Wi-Fi 6. And finally, on the client side, to conserve battery power, we had target wake time, which was a more effective way of managing the active and sleep cycles on the client side. So in a nutshell, we can see that Wi-Fi 6 tried to optimize the use of the radio resources by improving their spectral efficiency, by providing better scheduling flexibility, and also by adding support for the new band, which allowed us to provide higher bandwidth support in a practical deployment. So with Wi-Fi 7, now the focus kind of shifted back to enhancing the data rate. And one trigger for that is there's a strong competition, especially on the enterprise side from the 5G and the 4G front, where people are pitching private 5G as an alternative in enterprise networks. So Wi-Fi had to up its game. And that's where these requirements of supporting very high capacity very low latency, a large number of concurrent connections were really, the driving forces behind the new generation that is called Wi-Fi 7E, Wi-Fi 7 based on the 11B standard. And continuing from Wi-Fi 6, there's still a renewed focus on improving the spectral efficiency. So with these requirements, the standard came up with a set of enhancements, starting with the increased peak data rate. So going from close to 10 Gbps in Wi-Fi 6 to 23 Gbps in Wi-Fi 7. And this was brought about by two things. One was doubling the channel bandwidth, so going from 160 megahertz to 320 megahertz, which led to a direct, doubling of throughput. And second was a newer modulation scheme called 4K QAM, which allows us to pack even more bits per OFDM symbol. So with these two enhancements, we were able to push the data rate to more than twice what was possible in Wi-Fi 6. You might see in literature references to 46 Gbps as the peak throughput. That is possible only if you have 16 antennas or 16 special streams. And even though the standard has left the door open for supporting the 16 stream transmissions, but as far as the Wi-Fi Alliance spec for Wi-Fi 7 is concerned, we are still limited to 8 stream transmission, and that's where we say 23 Gbps can be supported using 8 special streams, a 320 megahertz channel, and 4K QAM modulation scheme. Now, it is not enough to pump up the data rate, because the ability to support such high data rates is limited to very specific scenarios, but the system should operate in a wide range of scenarios, and that's where the other enhancements of Wi-Fi 7 are really important. So the first enhancement we have feature is known as preamble puncturing. It was present to some extent in Wi-Fi 6 also, but not very useful the way it was designed. And if you look at wideband channels, especially 80 megahertz and 160 megahertz, there is always a risk that if you find a large or a wide channel available at some point of time, later on you might encounter some interference because somebody else put up another AP which is using the same channel as you. For example, here we see that an AP is operating on a 80 megahertz channel, and at some point of time start seeing strong interference on one of the component channels. So today, our options are limited to either I can reduce the bandwidth to 40 megahertz to avoid this interference, or I can switch to a different channel. Obviously, reducing the bandwidth means my throughput will go down by 50% in this case, and changing to another channel means disruption to clients, because they have to now reconnect, and some disruption will be observed. To address this, with the help of preamble puncturing, the AP can now selectively mute transmissions on parts of its operating bandwidth. So in this case, we can see that the AP can mute the third 20 megahertz channel and continue using the remaining 60 megahertz bandwidth. So even though there is a degradation in throughput, but that is less compared to falling back to 40. And also from a client's perspective, there is no impact because they continue to stay on the same channel. So this allows us to handle interference more gracefully, and as it has other advantages also, which we will see in a little bit. The second aspect or enhancement that I'm going to talk about is multi-RU allocation. So if we go back to Wi-Fi 6, where FDMA was introduced, which allowed a multi-user scheduling in frequency domain by subdividing the channel into smaller units known as RUs, and these RU sizes are expressed in terms of number of tones or number of subcarriers. So the smallest RU is 26 tones, which is roughly equal to 2 megahertz. So on a 20 megahertz channel, you could have 9 RUs, and you could allocate 1 RU per user. So you could send data to 9 users at the same time using a 20 megahertz channel. And there were other combinations of RU sizes and RU numbers depending on what was the channel bandwidth possible. But one big limitation of the OFDMA scheme in Wi-Fi 6 was that you could allocate only 1 RU per user. So if you had a scenario where the number of users was low or the demand was low, then you could see that some RUs were getting unused. For example, here we see that 3 RUs are getting allocated to users 1, 2, and 3, But because there is nobody else contending for resources, then the other two RUs are unallocated, which means you are wasting some of the frequency resources. And the other challenge was that different applications have different requirements in terms of packet sizes. And this rigid allocation scheme could not adapt to different application requirements. So because of this, there were challenges in using OFDMA with Wi-Fi 6. I mean, these were one of the challenges. There were other challenges, obviously, with OFDMA in Wi-Fi 6. What we have in Wi-Fi 7 is a more flexible allocation scheme where you can combine RUs. For example, if you see this 20 megahertz allocation where we have combined a 52 tone and a 26 tone RU to create a bigger resource chunk which can be allocated to the user. Similarly, at the bottom you see we have allocated a 26 tone and 106 tone RU to create an even bigger allocation. So by combining these resource units, we now have two advantages. One is you can adapt better to application requirements, and second is you can reduce wastage because now you can if you don't have enough clients, then you can allocate more resources to the clients which are contending for resources. Now, given that you have different bandwidths ranging from 20 megahertz all the way up to 320 megahertz, you can have a large number of possible RU combinations, which can add to a lot of complexity from an implementation and signaling perspective. So what the standard has done is to limit the number of possible combinations depending on what is the bandwidth you are using. So for example, for a 20 megahertz channel or a 40 megahertz channel, we are limited to only two possibilities where you can combine 52 plus 26 or you can combine 26 plus 106. Similarly, for higher bandwidths such as 80, 160 and beyond, again, there are a limited set of possibilities in terms of combining. But these address most of the practical use cases. So in that sense, this is a good trade-off between complexity and the flexibility in terms of how resources get allocated to users. It is important to note that we could use multi-RU allocation in non-OFDMA mode also, or you can say in OFDM mode or a single user mode where the entire channel is being allocated to a single user. So in this case, if you are, let's say, you have a lot of noise in one part of the 80 megahertz band or a 160 megahertz band, then you could allocate less than 180, for example, 160 or 140 to a single user by puncturing the noisy part of the channel. So in that sense, this is another enhancement with respect to Wi-Fi 7 and provides more flexibility in the way you allocate resources for multi-user and single user transmissions. The other big feature which we see, talked about a lot whenever we talk about Wi-Fi 7 is multi-link operation. If you look at the clients today, a large number of clients today or a large population of clients have multi-band support, which means that they can connect to either 2.4 gigahertz band or a 5 gigahertz band and with Wi-Fi 6, 6E, even 6 gigahertz band. But at any given time, the client is connected to only one radio of an access point. So this puts some constraints on, how efficiently we can use the available resources in terms of the different channels that are supported on the access point. With multi-band or a multi-link operation, now we have the flexibility to for a client to attach with multiple radios of an access point at the same time and choose which one to use dynamically depending on the capabilities of the client, as we will see in the next few slides. So the simplest mode of operation in MLO context is known as multi-link single radio. So think of a client which has multi-band capability supported on a single radio. So this client can associate with the access point over two or more links. So in this example, the client has associated with 2.4 and 5 with a multi-radio access point. But at any given point, the client will only use one of the operating bands, but it can switch in a semi-static fashion, you can say, to utilize the other band. If, for example, one of the bands becomes congested, it can switch to the other band. So this provides a flexibility in the way you utilize the available radio resources from the AP perspective. The second option that we have is known as enhanced multi-link single radio, or EMLSR. So here, if you have a multi-band single radio client, it can again associate with multiple radios of the access point at the same time. And it can also dynamically switch to choose which band it is going to operate on, almost on a per frame basis. So the way this is realized is if your client has multiple antennas, let's say it's a 2x2 client, then you can sense the channel, let's say on 2.4 gigahertz on one antenna, you can sense the channel on 5 gigahertz on another antenna. And the moment you find that, whichever channel is available, you can switch to 2x2 mode and continue your operations as on a single band. So this gives a more dynamic, you can say, switching across bands using this EMLSR mode of operation. Obviously, this also means that the client must have multi antenna capability, and it must also have be capable of switching very quickly from the sensing mode to the transmission or reception mode. So these are some of the implementation challenges that you can see in terms of how EMLSR can be realized in a real client. But the advantage, obviously, is that you are able to, very quickly switch across channels, which means that, whichever channel becomes available first, you can go there and transmit data or receive data, which means you can reduce the channel access delay in this scenario. The third, and you can say most complex version of MLO is known as multi-link multi-radio, where the client, if it has multiple radios, each of which can support a different frequency band, can associate with a multi-radio AP on all the supported bands and use all of them at the same time. It is similar to link aggregation in Ethernet world, where you could put two uplinks from an AP to a switch and utilize both of them at the same time for communicating on the wired side. So similarly here, the access point and client can use multiple links at the same time, which means that you have more bandwidth, more capacity, and you can push the per link data rates to a much higher level than what would be possible if you were using only one of the links at any point of time. Again, this means that the hardware on the client side must be capable of operating in this mode. So this requires some changes on the hardware side in order to realize MLMR mode. Within the MLMR mode, there are two possibilities in the way these different links operate. The asynchronous mode is where each link operates independently, which essentially means that you have two links which are contending independently for channel access, and once they get channel access, the link can go ahead and transmit. Similarly, the second link can also independently conduct channel access and start transmitting whenever the channel is available. So what it means is that there are scenarios where the two links can be operating in different modes, in the sense that AP1 may be transmitting. When I say AP1, this is one of the constituent APs in a multi-link AP. So AP1 could be transmitting on 2.4 gigahertz band, while AP2, which is co-located with AP1, could be receiving from another station on 5 gigahertz band. While this might be okay when you have a 2.4 and a 5 gigahertz scenario where one radio is transmitting, other radio is receiving, if we consider 5 gigahertz and 6 gigahertz, because they are very close together in terms of frequency separation, then this can lead to challenges because there could be self-interference. So this self-interference can be avoided by putting sufficient isolation between these two radios, which obviously means that from RF circuitry perspective, you need to have additional circuits to ensure this isolation is possible. The second option that we have is synchronous mode of operation, where the two links or the two radios on the EP side or on the station side, they coordinate such that the transmissions are synchronized and in the downlink, and the transmissions are synchronized also in the uplink. So this would avoid the problem of self-interference to a large extent, but it also means that you need tighter coordination across the radios. You also need to be, make sure that the way the MAC PDUs are created, they should align in the sense that the transmission and should start and end at the same time. And also the backoffs, which are integral part of channel access, have also to be managed very carefully, so that if one link finishes the backoff first, and while the second link is still waiting for their backoff timers to finish, then you have to pause until the other link is also ready for transmit, and then you start transmission. So there are challenges with respect to this, and there are obvious advantages, because now you don't need the same degree of isolation that you required in the case of asynchronous transmission. So there are, within the MLO, there are many complexities in the way these different modes will be implemented. And it will be interesting to see, particularly from the client side, what modes get enabled by handset vendors and chipset vendors, and that will really tell us how useful MLO will be in practice in the real world. So I just talked through some of the key enhancements of Wi-Fi 7. There are other things also which are part of Wi-Fi 7, but we don't have time to go into all the features. So we'll take a pause here. We can look at a couple of questions, Gabriel, before we move on to the next section.
Certainly, thank you, Nim. So we've had a few questions on the self-interference, which I think you sort of largely dealt with. So unless you want to add more there. I had a question on MLO. So you just mentioned there it's going to depend quite a lot on what's enabled in the clients, and we'll sort of see how that works out. At this stage, do you have a sort of a feel for, is MLO going to be more helpful as a sort of reliability, resilience play for links, or boosting capacity, or how do you think that's going to how do you think people are going to put this to use, I guess?
I think if you look at the three schemes I talked about, MLSR and EMLSR are really the simplest way you could implement MLO. And the real advantage of these two schemes is, one is you are able to reduce the channel access delay, because you can switch to whichever link is available and transmit your data, which means that for low latency applications this is really useful. And second use case I see is where the ability to switch bands also allows us to optimize the use of the radios on the AP side, because you may have a situation where let's say 2.4 is more loaded than 5, then you can transition the clients to 5. So that way you can steer the clients more effectively than was possible through the proprietary schemes that were implemented before MLO came into the picture. So I would say that initially these are in some sense you can call them low-hanging fruits that will be realized through the early implementations. But as implementations mature, we will see adoption of the more complex schemes like MLMR and EMLMR, which gives us additional flexibility in terms of aggregating bandwidth for when you have very high throughput requirements, or the ability to use wider bandwidths, for example, combining 5 gigahertz and 6 gigahertz to create wider channels. So for the high throughput requirements, MLMR obviously is the right choice, but that also is more complex to implement. So those will probably be available later, but MLSR and EMLSR are the ones which hopefully we will see on the client side much more quicker from an implementation perspective.
Yeah. Okay, good. And then one more before we move on. 4K QAM, 4096 QAM. I mean, perfect for capacity, but I imagine, and let's get your feedback. Very difficult to deliver in unlicensed bands with interference and so forth. What, practically speaking, do you think we'll be getting that and seeing that on devices?
Yeah. So the challenge with increasing the modulation order is that now your constellation is now packed with a lot of points. So the gap between 2 points on the constellation is now very, very small, which means that you need to have a really high signal to noise ratio in order to differentiate between the different points in the constellation. And specifically talking about 4K QAM, we are talking about SNRs of 40 dB and above, which are in practice, if you are very close to the access point, then yeah, you should be able to get it, right? So if I'm indoor, I am let's say I have a 4K QAM capable TV, then maybe that would work. with an access point, which is also supporting 4K QAM. But if I look at practical implementations, being able to realize this very high SNR is obviously a challenge. But we have a way to handle this by virtue of we have multiple antennas on the AP side. You could think of a scenario where if I have 4 antennas, I can use 2 special streams and use other 2 antennas for beamforming to improve the SNR. So there are ways around. You could handle the SNR requirements for 4K QAM. But yeah, if I look at the enterprise where the deployments can be dense and the interference can be high, probably less useful than the other features that we talked about in this section of the presentation.
Yeah. Okay, good stuff, Nadeem. I've moved you on to the next slide. There's a bunch of other questions in here, but I think they're going to fit better later on, and you're going to answer some of them, I'm pretty sure, as we go through here. So you're on to the next section. Take it away.
Yeah. Thanks, Gabriel. So now let's look at what are the problems that Wi-Fi 7 solves for the enterprise. So starting with support for higher capacity and higher client density, and to some extent also AP density. So as we saw that with 320 megahertz channel, you now get the twice the throughput compared to Wi-Fi 6, and you also have the ability to multiplex more users because now you have more RUs. So you could support a larger number of concurrent connections. And with 4K QAM, you get a 20% increase in the peak throughput, which means for the same amount of data, you consume less airtime, which means you free up resources for other users. So again, this means that you have the ability to support more concurrent users. On the MIMO front, again, because you have spatial multiplexing, so you can multiplex users now in frequency domain and spatial domain, which means that a large number of concurrent sessions can be supported by a combination of wider channel, 4K QAM, and MU MIMO. One caveat I would put here is with respect to 320 megahertz channel, if you look at 6 gigahertz today, in countries where the entire 1200 megahertz is available, you have 3 non-overlapping 320 megahertz channels. And in countries where you only have the lower 6 gigahertz available, you only get 1 320 megahertz channel. So there are challenges there, but we should see more possibilities of using 160 megahertz, which will be a big improvement compared to 80 megahertz that was possible with Wi-Fi 6, particularly in the 5 gigahertz band. When it comes to efficiency and reliability, multi-RU, obviously, as we saw, is able to support more flexible resource allocation as per user and application requirements. It also reduces the wastage when the demand is low. So in that sense, it improves the efficiency of the radio resource utilization. And puncturing allows us, first it increases the usability of wider channel bandwidths like 80 megahertz, 160 megahertz. And at the same time, it also provides a way to gracefully handle narrowband interference whenever we are using these wide channels like 80 and 160 megahertz. Potentially, you could also use puncturing as a means to manage or mitigate interference due to radars, because today we have to vacate the channel whenever there is a radar hit on any of the component channels. But with puncturing, it might be possible to just puncture the channel on which you see the radar activity and continue using the remaining channels. And MLO, as we saw, gives the possibility to utilize multiple links either together at the same time or dynamically switch between links based on application requirements, based on the available capacity, based on the congestion on the channel. So with these 3 features, we are able to support higher efficiency and also address the reliability requirements from an enterprise perspective. And when it comes to latency, this has been one of the challenges in Wi-Fi because of the way the protocol is designed. But once again, thanks to these new features that we just saw, especially with 4K QAM and MIMO and MLO, we are able to address the latency requirements to a large extent, especially with MLO, because the channel access delay is lower, because now you can sense multiple channels at the same time and switch to whichever channel is available, and then you can also switch channels based on congestion or lack of congestion or the available capacity on each supported channel. So we are able to manage the key requirements from enterprise using the features that we just talked about in the technical section of this presentation. But going beyond these generic requirements, let us also look at what are the specific applications which are driving various industry verticals and how Wi-Fi 7 is able to address them. So starting with the typical enterprise network, where we are seeing a lot more adoption of cloud-based productivity applications in the workplace, which means that users are trying to access applications like Google Drive or SharePoint and many other such applications. And there is, which means that a large number of users are accessing this at the same time. So obviously it means that users expect that in such scenarios, the latency, expectation is maintained. And also with this hybrid working that we are now used to, where sometimes we are working from home, sometimes we're working in the workplace, and most of the times we are collaborating with colleagues who are distributed. So collaborative working with rich telepresence is an emerging, you can say, application. And this is where high throughput is really important, and also low latency, in order to improve the interactivity of these collaborative applications. So obviously, as we saw, Wi-Fi 7 is able to support lower latency, higher throughput, and higher client density as well. So in that sense, it is well suited to the emerging requirements from an enterprise side. And if you look at the healthcare domain, where we have needs for a in-building communication network, which can be used by the hospital staff to communicate with each other. So in this scenario, unlike a typical enterprise, you will see a higher degree of mobility, because doctors, nurses, and staff are moving around, and a higher density of devices. People typically have many devices per user, and stringent latency requirements, especially when it comes to voice over Wi-Fi kind of applications, which are really important in this type of network. And then from a we see a lot more use of telemetry with respect to data being collected about patients through scans, through other machines, and this data has to be sent to some aggregation point where it can be analyzed for diagnostics and other reasons. And this application requires higher throughput because the amount of data is massive, and also high reliability, because we need to make sure that all this data gets pushed to the central repository in a reliable fashion. So again, similar requirements, but obviously some requirements are different, because this is a mission critical application. So high reliability is obviously very, very important in this context. And if you look at the industrial use case, there we are seeing emergence of devices, you can say, or autonomous robots, guided vehicles in warehouses, in manufacturing, and in other contexts. And this requires deterministic latency and ability to move seamlessly across a large industrial complex, such as a warehouse or a retail environment. And from an IoT perspective, because these tend to be large campuses, there's a requirement to support extended range, and also have a reduced power consumption on the battery powered devices, especially on IoT sensors side. And in a different context, with applications being built on top of AR, VR for design, for prototyping, and manufacturing, we also see demand for very high throughput applications and also deterministic latency to support these applications. And then coming to the campuses or educational environments, where digital classrooms are the norm. So we have expectations for high density in terms of clients, lower latency for these applications which are deployed in smart classrooms, and in other areas of the campus like hostels and auditoriums, again, higher capacity and high reliability, of course. And again, AR, VR is making a presence in terms of virtual labs. So similar requirements in the form of deterministic latency and higher throughput. Finance or banking is a slightly different application, because here reliability is very important, robust security is really important, and high resiliency is also essential. And when we look at people walking into branches trying to access the Wi-Fi network in the branch. So we need to be able to support a higher degree of security and also make it easier for the users to get onto the Wi-Fi network. So if we look at all these different verticals and the applications within these verticals, there are some common requirements like higher lower latency or higher throughput, and then there are also some application specific requirements, particularly for mission critical applications like reliability and resiliency. But from the the advancements we saw for Wi-Fi 7, we can say that Wi-Fi 7 is able to address most of these requirements in a very effective way. So in that sense, it is ready for meeting the challenges of the the applications across a whole range of industry verticals. Now the question is, how fast do we see Wi-Fi 7 taking up in the enterprise market? So this is driven by two factors. One is from the IP perspective, enterprise IP vendors, most of them have Wi-Fi 7 access points available, but that is not enough because we also need clients to be able to use all these advancements. And if you look at this data made available from Wi-Fi Alliance website, at the moment we have a pretty low, density or count of Wi-Fi 7 devices. But in the next couple of years, we will see a big population of Wi-Fi 7 devices available, which will allow us to use the Wi-Fi 7 infrastructure much more effectively, and we will really see the large-scale adoption of Wi-Fi 7 in the next 12 to 24 months when the device ecosystem matures and we have a wider range of devices available. Having said that, we are already seeing announcements from handset vendors for devices which are capable of Wi-Fi 7. For example, Apple recently announced the new iPhone will have Wi-Fi 7. Samsung already had a Wi-Fi 7 capable device. So there is more devices coming, but there's still some way to go before we hit the critical mass on the device side. So we will also look at from a network perspective, right? Wi-Fi is just one part of the network. There are other components as well. So if simply by replacing my older APs with Wi-Fi 7 APs is not going to solve all the problems. And we have to make sure that the whole network works together in order to address the challenges of enterprise access. So before we move on, I think we have a short poll for the audience. Over to you, Gabriel, again.
Yeah, we do. Thanks, Nadeem. So as you'll see, there's on your screen now, you should see our one and only audience poll question for the webinar, where we're asking which vertical, in your opinion, is likely to be the fastest adopter of Wi-Fi 7. And you can see there's 5 options and an other here. I'm going to hold it open just for a minute while people can vote. Also give Nadeem a little break on his voice. I think after this, we're going to have about 10 minutes to take us through the final section and some questions, Nadeem. While the votes are coming in, let me put a question to you, sort of essentially a business question. You talked about clients there, and obviously that's important. What's your sort of gut feel? How do you think what's going to trigger Wi-Fi 7 for operators? Versus a more Wi-Fi 6, a very capable technology. Do you get a sense from that there's a sort of demand trigger, or is it going to be more in the natural refresh of things?
I think it depends on the markets. If I look at it from a ISP or a telco use case where we have higher bandwidth available on the backhaul side, and in order to realize the benefits of a gigabit home broadband connection, you really need to have fast Wi-Fi also at home. So that is one of the drivers which we'll see a lot more traction, because of the ISP and or you can say the home market. If I look at the enterprise, then I would say this will be more application driven because some of the newer applications are more demanding, and they will really trigger the demand for the new generation of Wi-Fi because Wi-Fi 6 and 6E were adequate to address most of the basic requirements for enterprise Wi-Fi, but it's really the new applications which are going to drive the adoption of Wi-Fi 7 in the various verticals that we just talked about. Especially, where things like industrial, where we are looking at higher reliability, resiliency, more coverage, and also, applications like AR, VR, which really demand high bandwidth.
Yeah. Okay. There's going to be there's actually been a few questions on the industrial side, actually on narrowband applications of Wi-Fi 7, which if we have time we'll get to. People have been voting. Thanks. We've got a really good response here. Loads of votes and out of a pretty big audience. So I'm going to push these results live. And Nadeem, I'll just ask you what you think once we've all seen them. Here we go. Retail 27%, education 26%. Manufacturing 21, other 20, finance 6, government just the 1. That splits pretty well across our 5 sectors. Other than finance and government are a little lower here. Education, I guess, and retail, you get high density users. Nadeem.
Yeah, so education I think is not a surprise because this is an area where we are seeing strong investment in upgrading the facilities across campuses. In India and outside, so that's I think not a surprise to me. I think many verticals like finance went through an upgrade process very recently with 6 and 6E. So I'm not surprised that the numbers are less. And I think government also generally is a slow mover because there are a lot of compliances and other things that have to be in place before you get into federal procurement program. So it might take us some time. Honestly, I'm not very surprised with the
we've had a comment in actually. It says this is not a question but rather a comment, but I'll invite you to respond if you like, Nadeem. Just since Wi-Fi 7 and MLO mandates WPA3 only, there will be at least another year to deploy in bring your own device places like universities. Well-made point, I guess. Want to respond to it, or is it self-explanatory?
So actually, WPA3 was made mandatory for 6 gigahertz anyway. So with Wi-Fi 6E, WPA3 was mandatory. So in that sense, we already have a fairly large, population of devices which do support WPA3. In fact, with Wi-Fi 7, we have, additional, you can say, robustness added to WPA3. So I think that will obviously, take some time to come through. But WPA3 itself has been around now for, 3-4 years. So it's not new and devices already support it. Yeah. So I don't see that as a big challenge from adoption perspective.
Yeah. Okay, another comment coming in. Density is fine in education, but manufacturing will create a big revolution in Wi-Fi 7. I think that's just a comment someone's put in. Thanks. There's a bunch of questions here. Some of these are pretty technical and we're not going to have time to deal with them. But we asked Nadeem and his team to kind of have a look and get in touch with you after. Some of them, if we open up that technical topic, we're just going to be hours. But thanks for them, and also any comments coming in. We've only got a few minutes left. Why don't we do a question now then, Nadeem, as well? Since we have a lot of people writing in about the manufacturing sector, do you have any examples of use cases? And then the other one I wanted to get to, which Wi-Fi 7 features provide reliability for telemetry applications was one. There's a whole bunch of things essentially around industrial and, reliability in a nutshell.
So I think we have to look at it in 2 ways. One is, reliability in terms of, reducing the losses in some sense when you are transmitting over a shared medium. Right? So that is one part of reliability. And, if you look at Wi-Fi in industrial, generally there's a less of a coexistence problem because you have a large campus where you have your own Wi-Fis. So interference is not, from other DSS is not a big issue. But if you look at 6 gigahertz, there might be an issue because there are incumbents in 6 gigahertz, which are maybe, microwave links and other applications. But there, we already have regimes which are, allowing us to do better coexistence. I think the way reliability problem is getting addressed in 2 ways. One is, with MLO now we have the ability to choose the best channel. So let's say I'm operating on a 5 gigahertz and suddenly I find the packet loss is high, I can switch to 6 gigahertz, right? Or the other way around. Or if you have 2.4, you can switch to 5 or the other way around. So that way, you are more agile in the way you use the available spectrum or the available channel. So that gives us more flexibility in the way you adapt to interference scenarios. And then we have techniques like puncturing, which also allow us to handle interference much better than what was possible with earlier generations of Wi-Fi. And then
Cool.
finally, we have also other techniques in terms of dual modulation, diversity, which improves the reliability of the link itself at the physical layer.
Mm-hmm. Good stuff. Yeah, good stuff. Thanks, Nadeem. We've got 5 minutes left. So what I want to do, Nadeem, is give you, I mean, obviously this chart showing is pretty critical from my mind, where I started in the introduction. If you want to just take this chart and then follow through, there's a little bit of stuff on your dashboard and things. That'd be great just to take us through to the end. But we are on 5 minutes to go. Thank you.
Okay, I'll make it quick. So, I mean, this chart kind of illustrates what are the operational challenges that we, face from an enterprise networking perspective. So we already talked about, the new mode of working where people, are partly working from home, partly from the office, which poses, a different set of requirements. The use cases are evolving thanks to all the new technologies that are coming into the workplace. And we are seeing more devices per user. So there is increasing diversity of devices and increasing number of devices that connect to the network. And inherently, most enterprise networks are multi-vendor in nature, which means an additional layer of complexity from a manageability perspective. So really, from an enterprise side, the way to address this is to provide unified visibility across your network, across wireless and wired components, being able to drive, more workflows with automation so that you can have a nimble workforce and you are able to manage these complex networks more efficiently, and minimize the outages so that productivity loss is less and you are able to work better. And whenever issues arise, fix them quickly, most likely through automation and also through ML based techniques, so which reduces your MTTR. So in that sense, you have a more reliable end-to-end network. And within that context, I just wanted to quickly show you what we are trying to do. So within the HFCL enterprise solution, we obviously have a diverse portfolio of devices from Wi-Fi 5 to Wi-Fi 7, and also switches for PoE and non-PoE, and a centralized management interface which allows us to, customers to manage the networks, effectively and more efficiently. And also from an end user perspective, the ability to support different onboarding workflows for seamless mobility and secure mobility. And finally, being able to support the open Wi-Fi protocol stack, which gives more flexibility to the customers in order to decide whether what they want to run proprietary HFCL stack or the open Wi-Fi stack, which is vendor interoperable. So that is the way we are looking at solving the problems of enterprise Wi-Fi, and obviously the AI capabilities are an integral part of our offering.
Let's take another webinar, Nadeem, because there's tons here to get into.
I know.
Okay,
so we can take some more questions before we close.
Could we have a quick look at the console? I think that would be a great way to end. The next slide, I think.
Oh, you mean okay?
Yeah.
Yeah. So I mean the management system, we call it IO Canvas, is a single pane of glass management, which allows us to manage access points and switches from the same console. We have very flexible deployment options based on network sizes, what the customer requires, and integration with third-party components like captive portals and NAC is really essential because we have to interwork with existing network infrastructure. And the AI analytics part is really helping customers drive the operational expenses, because we are able to predict issues, we are able to help customers solve the problems faster, we can provide insights into what is going on, and you can really manage the network with a very small set of technical experts. So that's where the AI part comes in. And finally, I talked about very briefly in the beginning, there's a diverse range of products from mesh routers for the home all the way to high scale routers for the telco aggregation network. So in that sense, HFCL is covering all the bases when it comes to telecom and network equipment. So that's my
Perfect.
last
So
slide.
that's perfect, and that's a great place to end it. We have a minute, so I think just say terrific webinar. Great having you on. Like I said, I think there's tons more we could get into, but I'd just like to thank everybody in the audience for attending, asking questions, putting comments in. I think some of those we'll be able to follow up with offline. And then finally, to close out, a big thanks to Nadeem Atkar from HFCL. Great webinar, Nadeem. Thank you.
Thank you, Light Reading team and Gabriel in particular.
All right, with that, thank you very much and goodbye.
Thank you. Bye-bye.